I thank organizer of this meeting to invitation us to talk about this work, the generation of the microcosmic background and birefringence through the photon interacting with the axions, particles, sterile neutrino, and active neutrino. So these three type particle, axion-like particle, sterile neutrino, active neutrino, has parity-violating interacting with the photon. And this is exactly the topic of this conference. So in this work, we are going to show the three type of particles interacting, contributing to the CMB-cosmic birefringence. So CMB birefringence is an important observation and confirm major in observation. From theoretical point of view, this CMB birefringence is effect indicate the rotating of the linear polarization of CMB linear polarization plane of CMB photon. While he traveling this photon traveling from the last scattering surface to us, measured. And this rotating is measured by angle of how the linear polarization plane is rotated. And angle is indicated by beta, equation 1, and it's measured 3.342 degrees. So how this is related to the parity-violating? Because this measurement is done by the E mode and B mode of CMB. E mode is transformation under the parity transformation. The E mode is transferred as -1 to the L. Instead, the B mode is transferred as -1 L2 plus 1. So it's a difference. Then the closed power spectrum, E mode dot B mode, is parity-violating. This is very similar to the electric field and magnetic field. So the power spectrum, closed power spectrum CEBL, is measured, the no-zero value means the parity is violated because under the parity transformation, the E mode and B mode has a difference in size. So their closed power spectrum indicate parity-violating interacting of the photons traveling from last scattering spectrum surface to us. And this is what we are going to discuss today, what kind of three type of interacting. Active neutrino, sterile neutrino, axion neutrino, interacting with the photon, while the photon is traveling from the last scattering surface to us today, and we measure the parity-violating phenomena through this CMB birefringence phenomena. And here I call beta, the rotation angle of the linear polarization plane of the photon of CMB photon. So clearly, in order to create this no-zero CMB birefringence beta angle, photon need to have some interaction which violate parity-violating. So in literature, people study the interacting introduced by Hahn, which is not CMB violates Lorentz symmetry, CMB symmetry, CPT symmetry. So here in this article, we are going to discuss, as I repeat stress once more, the photon has three types of interacting with the sterile neutrino and active neutrino axions. And we know axion is a pseudo-scalar particle and which has parity-violating interaction with photon. Three types. And we will describe this in a consistent, in a one unified model, beyond a standard model. So this is the aim of these articles. And we know that all the active neutrino, we know which electroweak interactions violate symmetry, parity-violating, and axion we just explained is a pseudo-scalar particle, interact with photon, also is parity-violating. And now we are going to also describe this sterile neutrino, which also have left hand, right hand, different coupling to the photon. Okay, this is this paper we are going to say. Now, before we go to the microscope interacting photon, parity-violating photon with other particles, we describe this Birefringence phenomena. But this is usual in the textbook by the 4 stock parameter: total intensity, Q parameter, and U parameter, and circular polarization V. Okay, in terms of the linear polarization of the photon field at Ex, Ey. So we have a 4 stock parameter, Q, U, I, V. And normally, in order to study the Q is a linear polarization, U also is another direction linear polarization. So in order to describe this birefringence phenomena, people introduce this data parameter, data variable, and E mode and B mode is corresponding by this linear polarization U, Q, and U in equation 3 and 4. And this CMB photon in the polarization spaces, the density, ensemble this CMB from the density in the density operate in a polarization space is equation 5, and it is 2 by 2 matrix in terms of the 4 stock parameter. Then we want to see how this CMB photon traveling to see this stock parameter, how it's changing, how this linear polarization is changing, circular polarization changing, and also rotating, Faraday rotating angle of this plane or linear polarization is described by this Quantum Boltzmann equation. So all this reference is clearly cited in the paper. And this, once we know the density operate of in the polarization, we really can have all information about this, all the information about the polarization, circular polarization, and Faraday, these birefringence angles. So this equation, Quantum Boltzmann equation, is coupled with this interacting microscope interacting of interacting Hamiltonians. Okay, so we got to solve this Quantum Boltzmann equation to find the beta, which is angle of rotating angle or Faraday rotating angle linear polarization frame, and indicate the birefringence angles and measures. And in terms of E mode and B mode of the CMB photon, and as well as the non-zero closed power spectrum E mode, B mode correlation. Because if there's no parity violating interacting, E mode and parity is exactly symmetric. So E mode and B mode is no correlation. E closed power spectrum must be 0. So if there's a parity interacting, so E mode will exchange with the B mode, and the spectrum will be of the CMB in this angular spectrum of E mode, B mode will be correlated. So this is what is shown in equation 11, 12, and 13. So we see the last one, equation 13, is the closed power spectrum. It's very sensitive to the rotating Faraday to rotating angle of the birefringence rotating. Okay, and then the other is E mode correlation of the angular spectrum. So exactly we are focusing equation 13, and then equation 13 of closed power spectrum, and also this rotating angle of the CMB birefringence. Now let's turn to the microscopy interacting. So this microscopy is described by here. The part is described by equation 14, the beyond standard model, and it's a 4 4 sterile fermions interacting. Okay, why there's 4 fermions sterile interacting? Due to reasons. One possibly is due to quantum gravity effect. Introduce a so-called Thorson-free Einstein-Cartan Lagrange. Okay, this is a clear. It is studied in this reference. And the other thing is that the parity-violating standard model interacting found some inconsistency with this as a field theory. Need ultra-right cutoff. There's some inconsistency, which indicate theory beyond the standard model theory must be at the cutoff must be there sort of effective for fermion interacting. And then, in fact, from the other hand, we know Einstein-Cartan Lagrange from integrate heavy Thorson field, and we end up with this 4 fermion interacting. So now we just look at 4 fermion interacting, effect 4 fermion interacting of the steroids of the right-hand neutrino. Okay, this right-hand neutrino, 4 fermion interacting, undergoes the spontaneous symmetry breaking like Lambda-Nernst interact spontaneous symmetry breaking to generate top quark masses. Also, similarly, counterpart Higgs mechanism. This 4 fermion interacting of the right-hand fermion undergo the spontaneous symmetry break the lepton symmetry, global lepton symmetry, and generate the Majorana mass of the neutrino, sterile neutrino. And as a byproduct, there's a Goldstone. We know the Goldstone theorem. There's a Goldstone mode, which is a pseudo composite of the right-hand neutrino, and this exactly acts as like an axion. So the spontaneous symmetry breaking of this right-hand neutrino of this formula does 3 jobs. One is give us Majorana mass for sterile neutrino. The second is give zero mode or Goldstone mode, which is a pseudo composite of the right-hand neutrino. It acts as axion model. Axion, okay, axion. And the other one is a mastership scalar. It's like a scalar, like a Higgs field, but here we are not talking about this. So in the rest of the article, we focus on this axion produced by spontaneous symmetry breaking of the right-hand neutrino in 4 fermion interacting this type, and play the role of the axion. And beside this axion produced, generated is coupled to the standard model particle, and effect induce effect interacting of the W boson, a standard model W boson, interacting with the right-hand particle, because we know the standard model W boson is only interacting with the left-hand particle. But here, because of this 4 fermion interacting of the right-hand neutrino, introduce the W boson interacting with right-hand particle with a very small coupling constant GR, which is about 10 to the minus 4 we were talking about. And rest of also introduce effective coupling, which is represented by one particle irreducible vortexes, and of course mass at low energy is very small, and then is consistent with the standard model in the low energy. However, in a high energy, this coupling could be very big, and then parity symmetry can be restored. But we are not focused on this. The old article has discussed about this. Today we are talking about birefringence phenomenon. So this effective coupling means that W and G and photon of the standard model gauge boson, they are interacting right-handed sector of neutrino. Okay, this is absent in the standard model. So we consider this as effective operator to study this birefringence phenomenon. And clearly, the parity symmetry is violated, and how much violated is measured by this right-hand coupling GR. And this not for study, the birefringence phenomenon is not first time we study using this effect of Lagrange. Actually, we have studied vector boson fusion, and double beta decay, and axion gyno experiment for dark matter, and also astrophysics observation. All these references are being listed, and result indicate this right-hand coupling means standard model gauge boson interacting with right-hand particle sector are very small and consistent with low energy limit observed in the low energy of the standard model. So now today we go ahead, and then this right-hand neutrino can be a candidate of dark matter. Okay, that's why we say sterilized neutrino, which is a candidate of dark matter, and however, he's still very thin interacting with CMB photon. Let's by photon, the CMB photon acquired a contribution to birefringence effect. Okay, so this right-hand particle has a long lifetime, which estimate in another Jacob particles, and then we estimate this bound by this as a dark matter candidate of the sterile neutrino. The GR has to be smaller than this, 18. Otherwise, it will decay and cannot be a candidate of the standard dark matter particle. So now we go on to see how the sterilized neutrino contribute to the cosmic birefringence parameter beta, and which actually this has been calculated in active neutrino. The beta is equal to 1/2 of the opacity of this particle interacting with this photon interacting this particle, like active neutrino, and sterile neutrino, and axions. So this opacity is a question we are going to compute it, and to see to relate to beta, which is major. So we compute the sterile neutrino opacity, and also we compute the active neutrino opacity. Okay, and this computation is complicated. Need to compute all these box like Feynman diagram, and compute Quantum Boltzmann equation contribution, and to see how much it can contribute to the beta. Okay, so recall we have two type of. First, we compute two type of the contribution. Okay, and then the conclusion we found is the sterile neutrino contribution is very small, much small, should be neglectable. The more important is the active neutrino. And we go on to calculate also the axion neutrino, axion interacting with a photon in parity-violating, okay, through these equations, okay, through this equation and this Quantum Boltzmann equation 39, and we see how this axion contribute to the parity-violating parameter beta birefringence 1 is equation 41, which is the value of the axion in the last scattering and today. And the parameter here is axion coupling. Axion coupling is like we calculated, and in this model is related to equation 24. And finally, we are going to resolve. Finally, we see give the parameter constraint and parameter in this axion parameter space and so on, and we see discuss this the parameter constraint parameter space, and also we give the close power spectrum we find in lower angular momentum. The axion contribution is important to discuss. So important to discuss, and this I think is, and I have no time, I run out of time. So thank you for attention, and this figure is close spectrum to see how the axion is contribute to the CMB close spectrum. So thank you very much for listening, and I invite you to read the article, and I think I run out of time, and I stop